So today the class will be started formally today is that I will be teaching you about what is algorithm. So do any people or any student want to tell me in your opinion or from your side is what will you learn in these classes? Don't tell me you are coming to this course to learn algorithm. That's the course's name. So do any of you want to tell me what can you learn or what is the design of the class?
Making multiple sense of the wave conversion or input to output.
Okay.
For example, like equation or sequence.
Sequence equation. Any other answers? So the first question is, what do you think you can learn from the class? Or what is the difference between this class and data structure? Optimization. Good answer. Other opinion? Or you can just tell me that you don't know what to learn from these classes. What do you expect to learn from these classes? That is the course's name. Yeah, like specific way to solve problems. Right? So in these courses that you may think, some people may think that perhaps we will be in the computer, that in the computer classroom that we are programming in these courses. But that is not what this course will be taught you, because that this course is not telling you how to program, but it is a class to help you to enhance your programming skills. Okay. So keep this question in your mind that perhaps after this class you will know what are we going to learn in this class. So the first class. So there are the second question and the third question. The second question is that what is algorithm? And the third question is what is programming? So that's what I'm going to teach you today. So what is algorithm? What is algorithm? Wait. Real quick. Okay. Any structure to solve a problem. Good. Mathematical. Yeah. Good answer. Any other opinion? So Anjie. Okay. What is algorithm?
It's like a step-by-step procedure to efficiently process information.
Perfect. That is a good answer. So whenever to ask you what is algorithm and what is programming, the most important thing is that we need to define what are you going to learn or what is the definition of algorithm. So there are many algorithms that we are using in these daily lives. Is that when you look up to your cell phone, you may be waiting for your perhaps your girlfriend or your father's or mother's for some message, and your email app will source the new message into folders, and that's an algorithm. And when your phone gives you direction, like Google Map, it follows the direction, it follows the algorithm for the optimization to tell you which direction or what is the optimal path for you to go to the destination. That is what we are using algorithm in our daily lives. And whenever we are making tea, do you drink tea? Or you just go to 7-Eleven to buy it? So whenever you're making the tea, you may boil the water and place a tea bag in the cup, pour the hot water over the tea and steep the tea and add milk if you want the milk tea. That is also an algorithm. So you can see that an algorithm requires a precisely step-by-step procedure. And that is called a sequence of different actions. We got clear steps and decisions based on different conditions. So what is the algorithm? We got precise step-by-step plan for computational procedure. Therefore, when speaking of algorithm, there are four main topics four main parts that we need to consider in the first place. The first part will be we need a goal. Because we want to find solutions, we need a goal. So the first one is goal identification. When it is like you want to maximize or minimize. You want to maximize or minimize the problem or the decision problem you are going to solve. And we got the initial state is that we got the first step and we want to use the algorithm to improve each step or each iteration. And then we will got the third part of control search process. And we will be the finiteness is that the algorithm, you don't want an algorithm that perhaps you are writing a while loop and the algorithm won't just stop it. So the question is how are you able or how do you search on the state space? So there are two parts that we need to consider. The first one is the intensification, and the second part will be the diversification. The intensification may be like you are searching the area or the solution of the area, you just go straight through the end. That is called the intensification. You want to condense or you want to converge your solution. That is called intensification. And the diversification is that you want to span your area or you want to collect more solutions or collect more possible scenarios from the searching procedure. So in that case, you will, for the diversification, you spend your ways to search the solutions set. So whenever we talk about algorithm, we need an input. You need to know which data or what data you want to collect. So from the first side, you need the data which the algorithm needs to process to produce the desired output. And then we got the algorithm. The is a precise step-by-step procedure to tell you or to help you to search the optimal solution. And finally, we got the output of the result or the solution produced after the searching process. So the next part is what is programming? Do you know the difference between programming and algorithm? Yeah. So 小恩 What is programming? Writing code. Yeah. Good answer. And another is, let me ask, 乐声. Okay. What is programming? Solving the problem. You call solving a problem programming. Okay. Good answer too. Make. 日光 make. Bo xi. Okay.
Solving a problem in
Okay, you can think about it. Okay, so whenever talking about programming, sometimes you may be confused is that it seems that there is no difference between programming and algorithm. In fact, there are some differences. Is that programming equals the algorithms and data set, adding data structure. That is why there are courses called data structure, and there is a class called algorithm, and that is after that you will know what does programming means. In data structure, you need to know what data you are going to solve. You need to process or you need to design a good data structure for programming. And another way is that whenever we are writing the code or we are designing a procedure, you will need an algorithm to help you to solve problems, and that is the so-called programming. Okay? So in this process, we will not go to the computer class or ask you to bring a computer to this class. It is because you may learn the programming part, how to program like C, C++, C# or Python, Java in data structure or GUI. And another part is that in this process, I will be teaching you what is the algorithm. So it will be much more like a math class because we will start by the matrix operation, like linear algebra, and then we got linear programming. Have you taken the courses called linear algebra? Yep. Lots of proving, right? Telling you to calculate the matrix and telling you that after the classes you think you learned nothing but but all the difficult exam, right? Yeah, and that's what I have learned in my student career. I got the same problem. But whenever you go to that, and that's why they call the fundamental courses, is that whenever you go to see the like discrete math and linear algebra, you may think when you're learning it, it is very, you suffer from the class, and then you think that it is quite useless. But whenever you come to another class, you think that, wow, that is the fundamental idea, or there are some fundamental concepts you need to learn from that course, so that it helps you, but enables you to learn another courses more easily. So linear algebra provides a way to teach you how to view the matrix or the matrix operations more easily, so that you can solve linear programming problems. And whenever we are talking about algorithm, every problem should and need or is required to be formulated by math problems. If a problem cannot be transformed into a mathematical way, it cannot be solved by the algorithm. For example, what do you want to eat for your breakfast? Can you solve that by algorithm? No, yes, you can. We are using the GPT or the LLM. No, yes, you can. But in the past few days or in the past decades, you are not available to solve that. But even in GPT or in the LLM, those problems are able to solve you are able to formulate the problem into a mathematical way. And in LLM, they are solving the problem by the concept of possibilities and in different distributions. Okay. So I think in next week I will start it will be like much more like a math class. Quite boring, so if you want to come, just come. Very boring, or if you already know how to, if you got a good grade in linear algebra, I don't think you need to learn next course. And then it takes about nearly a week to teach you about matrix operation. And after that, we will start by linear programming. In your senior high school, it is the course is like what you have been taken in senior high school. It's like you are creating the mathematical way, a mathematical model, and you are finding the optimal solution. It may be the maximization or the minimization for the problem. And then we will go through some classic problems in algorithms like sorting or like scheduling or dispatching. And I will use some cases to teach you how are we able to formulate the problems, practical problems into mathematical models. And then you will find out that it is not a good way always to use mathematical model to solve the problems because there are NP-completeness problems. You can use the mathematical way to build the model, but it is not efficiency to use the mathematical model for some programs like Lingo or Cplex or Groovy to solve the problems because it is too complex. You are not available to find out the solution in a reasonable time. So then you need to develop heuristic algorithms. Then in data structure, you have learned a lot of heuristic algorithms. But in the practical way, heuristic algorithms may be confined or they are limited to many cases. And therefore, we will go through the main heuristics. Is the so-called, now we call that in like soft computing. And the most important thing about meta heuristic is how you are able to solve the problem and how you are going to design the encoding and the coding procedure of your soft computing problems or your soft computing algorithms. Okay. So let's come to this class. So whenever we talk about programming, it will be like regarding software creation. We need to identify the requirement of a program, and we need to translate the requirement into code. And you need to start debugging because it is quite hard to just write a program without any bug. That is quite difficult unless you are a genius. And then we start testing. Testing is like there are two parts about testing. The first one will be the replication test. Is that you need to ensure whenever the same data set you put in the algorithm, you got the same good solution. That is called the replication testing. And the next part will be the robustness test. Is that whenever you are given the different scenarios or you design many different types of scenarios to the algorithm, they give you a good enough solution that you may be satisfied. That is the testing part. And then we need to create documentation because nowadays, you are not writing a code for yourself. You need the teamwork. So you need to create documentation, and there will be more. And as for the part of coding coding is just a subset of programming. You are just writing lines, you are writing the machine readable inputs, and you need to choose a good programming language, and you can solve the problem. So informally, algorithm is, you can say that algorithm is any well-defined computational procedure that takes some value or sets of value as input and procedure, produce some values as output. And an algorithm is thus a sequence of computational steps that transform the input to the output. So it is. So you can see that what we want to do for the algorithm is that it requires an input that we can define it by x. And after the procedure, we call f of x. You will get f of x. And it is quite easy to define the algorithm like this. So you can see that it is just a procedure telling you to transform x to f of x. So that is algorithm. Very, very easy. So whenever that you got x1, x2 to xn, and what you want to do is to summarize xn. And you call that the algorithm? Sure. Any calculation that transforms the input to output, and you got a precise procedure, you got a precise iteration, that you can call that an algorithm, even though the relation way. So that we can view an algorithm as a tool. We can view an algorithm as a tool for solving a well-specified computational problem. And the statement of the problem specifies in general terms and desired input-output relationship. And the algorithm describes a specific computational procedure for achieving your expected output. So here comes. Then quite easy example is that we will use the sorting problem for instance. So I think that when even in like GGuide or data structure, the classic problem is sorting, right? The first algorithm you have been like okay. So if we want to solve the sorting problem, we might need to sort a sequence of numbers into the decreasing order, so that the problem arises frequently in practice and provides a ground for introducing many standard design technique and analysis tools. And here is how we define the sorting problem. Is that we got a sequence of n numbers, like A1 to AN. And as for the output, we got a permutation after reordering. So that we got A1 prime, A2 prime to the AN prime of the input sequence, such that we can find out that A1 prime is smaller or equal than A2 prime until AN prime. So, for example, given the input sequence, like 31, 41, 59, 26, 47, and 40, 41, 58, a sorting algorithm. And what we expected is that we want to find out from the smallest to the largest number. And such an input sequence is called an instance of the solving problem. And in general, an instance of a problem consists of the input that satisfy whatever constraints are imposed to in the problem statement need to be computed a solution to the problem. So can you tell me that, or can you tell an algorithm is correct or not? Of course, yes, it is that. Since that there will be the correct or the incorrect answer of the math problem, right? So that the algorithm is solving a math problem, so that you can say that the algorithm is correct or incorrect, or you can say that the algorithm is efficient or inefficient. So how do you define the algorithm is correct? Is that like I have told you, the robustness test, whenever an algorithm is said to be correct, in every instance, the input instance, it shows the correct answer. And in that cases, we say that your algorithm is quite correct. And whenever you find out an example that may not satisfy your algorithm or cannot satisfy the equation in your mathematical problem, we say that the algorithm is incorrect. And an algorithm can be specified in English as a computer program or even as a hardware design. The only requirement is that the specification must provide a precise description of the computational procedure to be followed. So what kinds of the problem can be solved by algorithms? I think there are some parts of like biology is that our DNA sequence is quite complicated, right? We've got millions or billions of different combinations of our DNA sequence. But from those biologists, they want to manage and they want to analyze the different possibilities or different scenarios of DNA sequence. They will need algorithms to help them. And the internet, if you want to find the best route for data transmission and enabling search engines to retrieve information quickly. And as for the part of e-commerce, is that what we are using these days, we also need algorithm. And for the most important way or the most important part is about business and manufacturing. And it is also what you may be doing in the future. I don't think there are people going to be a biologist in this class in the future, right? So you may go to the commerce company or the business or for the manufacturing side. So, but let me ask you a quite interesting question is, have you ever think of what you are going to do in the future? Perhaps 5 years or 10 years later. What do you want? Since you are coming to the computer science, and what do you want? You want to go to Meta? Or like the, you got to put it on your phone. So, okay. So, raise your hand if you want to go to the like Meta in the future. Nobody wants to go to Meta. The last time I asked students this question, I think 70% of my students raise their hand if they want to go to Meta. So I'm quite curious, what company or what field do you want to go in the future? Or you just want to win the lottery and then you do nothing in the rest of your life? That is a dream, not your career path. Okay, what do you want to do in the future? Open source. Okay. So, and how many of you raise your hand if you want to conduct like the software design in your future? Nobody? Okay, good. Okay. And how many of you want to dedicate yourself in manufacturing, like semiconductor? Since that we all know that Taiwan's famous, we got our TSMC, and we got a lot of good semiconductor companies. So good. But whenever I told my students if they want to go to those semiconductor companies, you can go to IT. or or another department called Computer Integrated Manufacturing Department. That is a good field for students in computer science to go to. They are running algorithms to solve the problems like productivity optimization and to enhance the yield rate for the company. And that will be relatively interesting if you want to dedicate yourself in manufacturing. You don't want to go to the manufacturing side and then as like an operator. That is not what we are doing. Okay. So let's come to our class. How are we able to define specific class problems? The main idea is to give concrete examples, and the text introduces 4 specific computational problems covered later in the book or in the courses. Is that there are some specific classic problems like shortest path problem, the longest common sequence, the topological sorting, and the convex form. Well, the first question is that we are finding the most efficient route between 2 intersections on the roadmap, like Google Map. And as for the second problem, is that we compare two sequence like DNA standards or like DNA sequence to measure the similarity. And the third part will be like the topological sorting is to determine the correct order of tasks, when some parts depend on the completion of others. And as for the convex form, it is much more like what you see in linear algebra or like in linear programming. You need to find the smallest convex boundary that encloses a set of points, like a type of rubber band around the nails. So here is another side of how we are able to define the problems. And defining the problem is I think it is one of the most important things you need to learn from these courses. And that's what I have told my students. You can ask the TA, is that I don't really care how many, I think the fantastic or how many interesting algorithms you are using in the future. But what we may be interested is that what problem you are solving. So based on the problem, you design an algorithm. That is the way, that is the fundamental goal, is that you are designing an algorithm to solve problems, not you are designing an algorithm just because it is fun. So a well-structured problems is what you can use algorithm to solve. So there are many, I think that in the future after graduating, or you may not be graduated, I don't know. So after you graduate from NCKU, you may be a graduate student or even a PhD student. And after you finish your PhD career or the graduate career, you may go to the company. So there are lots of problems that need to be solved. But whenever your boss or your manager asks you to solve a problem and tell you to design an algorithm to solve the problem, the first thing you need to know is that whether the problem can be solved by an algorithm or not. The first thing you need to do is not start programming, because you may not solve the problem, because the problem may be the ill-structured problem. So there are 2 kinds of problems. The first one will be well-structured problems, and the second part will be ill-structured problems. So what is a well-structured problems? Is that you can use mathematical way like what I have told you in the beginning of the class. Is that you can use mathematical modeling to formulate the problem. And as for the ill-structured problems, there are uncertainties or there are some tasks that requires decision makers to do by the so-called human intelligence. We got artificial intelligence and we also got the human intelligence. Okay. So for example, for the world structural problems, there are checkers or weiqi or the Tao or chess or theory provide proving. That is the world structural problems. And as for the real structural problems, like you are conducting a cooperative planning in business or management and document and music composition. That is called the illustrative problems. So there are some common characteristics of these problems. The first part will be to overwhelming the number of candidate solutions. There are simply too many possibilities to check them one by one. So you need a clever algorithm to find the best solution efficiently. And there are two parts in considering these problems. Is that you can, so there is a concept called optimization or a near optimal solution. Okay. So when we talk about algorithm, the problem we are going to solve, like I have said, we can change it into a mathematical model. So the math model will be either maximization or minimization. And then we design an algorithm. Then we design an algorithm to solve these two problems. And then OK， 把它调高个2度。Whether we design an algorithm to solve the maximization problem or a minimization problem. And in that case, there will be different solutions and there will be different parts or like different scenarios. So if I tell you to solve a problem, a maximization or a minimization problem by using the algorithm, you got like this problem. Like this problem. What are we expected? What do we expect? We are expected to find the summation of x, and we are expected to find decision variables of x. That is what we expect. But however, in practical way, to consider a problem in a practical way is that what can we find in the real world? You design an algorithm, but if the algorithm is efficient, well here comes if the algorithm is efficient. or individual. There will be several results. The first result is that you can find the optimal solution. You can find the optimal solution. What is an optimal solution? Is that the decision variable you find out that in the overall solution space, you cannot find the better solution with the X. So that is called we find the optimal solution of your algorithm. We design an optimization algorithm. And another one is that we are finding the near optimal solution. Of course, we want to find an optimal solution, but it may you may take you a lot of time complexity. Like an NP-hot problem. Okay. So you may not always find the optimal solution with your algorithm. You may find an optimal, near optimal solution. So they will be heuristic. Or meta-heuristic. Okay. So the result might be in two phases. And these two, either way, will be a good solution. But the worst case is that you fail to find any solution. So from the next week, we are going to teach you about matrix operation, and we will go through the linear programming. It's from the side of optimal solution. And whenever, so here is linear programming. And then we got like simplex method. Or other algorithms teaching you to use solution. And there are different software like Lingo or Sequence or Ruby and so on. They are teaching you to find they are supporting you to find the optimal solution. But as I said, the time complexity is relatively high, and you are not always to solve the problem by using the optimal solution or by using the optimal algorithm. And therefore, to compensate the problem, or you still want to solve the problem, so you need to define or you need to design the algorithm to find the near optimal solution to be much more efficient. So in these courses, I will be teaching you the part of heuristic and meta-heuristic after the approximation algorithm. So let's come to so whenever you design an algorithm, we need to ensure the practical value of the designed algorithm. And what you want to do is not only solving the problem, but you want to save time. You want to save human effort. And the most important thing is that you want to save money. For example, a trucking company saves a fuel cost by finding the shortest path. And that's the value of developing algorithm. And I think we will stop here, and after I think 20 minutes, we will begin our class again. Okay? Let's take a break. Okay, okay, okay. Let's come to our class. Let's come to our foreign class, okay? So, after the first class, I think today is our first class, right? So, after our first class, any opinion or any suggestions? The class is too early in the morning. Yes. Yeah, it balances me as well. So, any suggestions? Don't tell me it is too early in the morning. I cannot change that. Or, yeah. Okay. Or you want to change the time for signing for the class if perhaps in the second in at 10对你们好一点好吗？还是你们想要把点名的时间改到第二堂课？Did any of you want to change the time for signing your name for the class? Raise your hand if you want to. Perhaps at this time. So if you don't raise your hand, TA. No. Okay, because if from my opinion, if you are too tired and you are riding the scooter or the motorcycle to our school and any accident happens, that's not what I want to see. Okay, so for the next classes, you will need to sign your name at this time, okay? So if you don't want to come for the first class, just feel free. But if you think that you can learn something important in your life, or not in your life, if you can learn something that is beneficial to yourself, then you can come. You can come for the first class. But of course, I will come for the first class. I'm your teacher. Okay. So any suggestions or not? Or do you have any suggestions for the class? Okay, so from my side is that if you are, I think it is to take this class is that one thing is the most important is that if you do not do something that against school's regulation, and if you just follow the rules, follow my rules, and I think your grade will not be too bad. So you can be confident to your grade, because I know a lot of you may want to go study abroad in the future. So I may be nasty sometimes, but for the grades it will be very sweet. Okay, then let's start this class. So okay. Let's come back to teach you about the role of algorithm in computing. So here are some characteristics of these problems. Oh, I finished this one. Okay. So whenever we want to design an algorithm as a technology, is that we are supposed that computers were infinitely fast and the computation and the computer memory was free. Whenever we want to design the algorithm, you need to think about it as an assumption, is that the computers, the resource of this hardware is always enough for you, so that you can develop an algorithm for optimization in the first place. And when you find out that the not fast enough, or your computing resource is not enough for you to solve the problem. And at this moment, you develop or you change the algorithm. But in the first place, we always want to define or we want to find the optimal strategy to design an algorithm. Okay. So in that case, or consider one question is that our computing power is getting stronger and stronger these days. Like since that we got the media and we got a lot of that. Nowadays, the trend of the technology migration turns towards like the more than more migration. So that is it still necessary for us to learn algorithm or not? The answer is yes. If for no other reason that you would like to demonstrate that your solution method terminates and do so in the correct answer, because we always need to find the correct answer. And then algorithm is a way to support you to find the correct answer if you want to solve the problem in a practical way, and not by the human intelligence, but by the artificial intelligence. Okay. So if computers were infinitely fast and any correct method for solving the problem will do, you will probably want your implementation to be within the bounds of good software engineering practice. For example, your implementation should be well designed and documented, but you would most often use whichever method was the earliest to implement. And of course, computers may be fast, but they are not finitely fast. And memory may be inexpensive, but it is not free as well. So computing time is therefore a bounded resource, and so is based in the memory. So you should use this resource wisely. And algorithms that are efficient in terms of time or space will help you to do so. And that is the reason that you need to learn algorithm. So whenever we consider algorithm, the most important thing is to be correct or not. You need to find the correct answer. And the second part is about the efficiency. Is that different algorithms are devised to solve the same problem, often differ dramatically in their efficiency. And these differences can be much more significant than differences due to the hardware and software. As an example, we see two algorithms for sorting. We got the insertion sort, we got the merge sort. For the part of insertion sort, it takes time roughly equal to C1n squared to sort n items, where C1 is a constant that does not depend on n. That is, it takes time roughly proportional to n squared. And as for the part of merge sort, it takes time roughly equal to C2 n log n, where log n stands for C squared is another constant that also does not depend on n. And as for the part of the algorithm, as another part is that the insertion sort typically has a smaller constant factor than merge sort. So when C1 is smaller than C2, we shall see that the constant factor can have far less than an impact on the running time than the dependency on this input size n. And let's write the insertion sort running time as C1n squared, and the merge sort runs as C2n log n. And then we can see that the insertion sort has a factor n in its running time. Merge sort has a factor of log n, which is much more slower. So on this side, we can see that since that we want to solve the algorithm in a much more efficient way to save time, to save your computing resources, that finding or designing an algorithm that is much more efficient is one of the most important things to find it is another important thing to solve the problem. And although the insertion sort usually runs faster than merge sort for small input size, once the input size n becomes large enough, you can see that it will be much more powerful to use that algorithm rather than the original one. No matter how much smaller C1 is than C2, there will always be a crossover point beyond which merge sort is faster. And as for the part of a concrete example, let us take a faster computer A and a computer B. As for the code of computer A running insertion sort against the slower computer B running a merge sort, then each of them must sort an array of 10 billion numbers. And suppose that the computer executes 10 billion instructions per second, and computer B executes only 10 million instructions per second. So that computer A is 1,000 times faster than computer B in raw computing power. And to make difference even more dramatically, suppose that the world's craziest programmer calls insertion sort in machine language from computer A, and the resulting code is 2n squared instructions to sort n numbers. Suppose further that just an average programmer implements merge sort that is using a high-level language with an efficient compiler, with a resulting code that 50n log n instructions to sort 10 million numbers that you can find out that computer A takes 20,000 seconds. Is that you just need to put the value inside, and you can calculate how many times it takes. And as for another B, when you put the value inside, you can get 1,163 seconds. So that is the power of designing the appropriate algorithm. Whenever you find or whenever you design the predictive algorithm, it helps you to save the time. And from the practical use in industry, you need to save time because nowadays these algorithms or these manufacturing fields, it requires a lot of time. It requires decision makers to make decisions like scheduling or like the run control, virtual metrology. It requires a fast response so that the machine can conduct self-adapting, self-configuration to support decision making in advanced planning systems. So it is very important to design appropriate algorithm in computing. By using an algorithm whose running time grows more slowly, even with a full compiler, computer B runs more than 7 times faster than computer A. And that means if you've got a computer that is not good enough, or if your professor is poor and he is not available to provide you with efficient GPU for you to solve the problem, the most important thing is that you need to design a good algorithm to support finish your thesis. That is very important because our resource may not always be enough. Even though you can see NVIDIA, they are designing good GPU, but if you are not wealthy enough to buy those GPUs, what are you going to do? And if you don't go to those good enough companies, if perhaps you are just in the medium-sized company, they are not always wealthy enough to provide you with the best resources, and you still need to solve the problems. So at this moment, you need to design an algorithm that provides much more efficient way to solve the problem. And that's why it is very important to design good algorithms rather than instead of just buying good computers or buying good GPUs. And the advantage of let's come back to the slides. The advantage of the merge sort is even more pronounced when we sort 1,000,000 numbers. When insertion sort takes more than 22 days, and the merge sort takes only under 4 hours. So in general, whenever the problem size increases, so does the relative advantage of merge sort. You're going. Okay. So in data structure, you can see that a bad algorithm makes your time complexity grows exponentially if you didn't design it well. And however, if an algorithm is designed good enough, it helps you to save the time exponentially as well. So that is one of the most important things in algorithm. So here are some examples to show you that we should consider algorithms like computing hardware as a technology. The first thing is that the total system performance depends on choosing efficient algorithm as much as in choosing fast hardware. Just a rapid advance of being made in other computer technology, they are being able to make in algorithms as well. And you may wonder if that these algorithms are truly that important on contemporary computers in light of other advanced technologies, such as we want to have some advanced computer architectures and fabrication technologies. And as for GUIs, and there will be like objective-oriented systems, and we want to integrate web technologies and fast networking, and both wired and wireless. Fast networking, both wired and wireless. So, although there are some applications that do not explicitly require algorithm, for example, when we consider a web-based service that determines how to travel from one location to another, its implementation would rely on fabric hardware, a graphical user interface, wide area networking, and so possibility possibly on object orientation. However, it would require algorithms for certain operations, such as you want to find optimal routes that one that perhaps like a shortest path algorithm, render maps and interpolating addresses. And there are some parts that we need to consider as well, is that even an application that does not require algorithm context, and the application level relies on heavy on algorithms. The first one is that does the application rely on fast hardware, and the hardware design use algorithms. And the second part is that does the application rely on graphical user interfaces? The design of any GUI relies on algorithms as well. And does the application rely on networking? Routing networks also relies on addresses. And does the application written in language or other machine code? You also need algorithms. So algorithms are the core of the most technology used in complementary computers. Okay. So furthermore, with the ever-increasing capacities of computers, we use them to solve larger problems even than before. And as we saw in the above comparison between insertion, sort, and merge sort, it is a larger problem size that the difference in efficiency between algorithms become particularly prominent. Having a solid base of algorithm knowledge and the technique is one characteristic that separates the truly skilled programmers from the novices. With modern computing technology, you can accomplish some tasks without knowing much about algorithms. But with a good background of algorithms, you can solve problems much more efficiently. And the most important thing is that you are able to know what you are doing and what problem you are going to solve. And it helps you to train your brain. So I think I have spent some time teaching you about what the importance of algorithms, and I just finished reading the slides. So here comes the part of the definition and some notations that we will be used in this course, and it is a little bit similar like you have been taught in data structure. Is that we will start by teaching you about the time complexity and the notations that will be used in time complexity. So at this point is that the most important thing is how we are able to evaluate an algorithm is the efficiency and the correctness. So to measure the efficiency or the performance of the algorithm, we need a well-formulated way to do so. So the best way to describe the behavior of the function in the limit is that we need to study the asymptotic efficiency. And there are some notations that we need to use, and we need to compare two different algorithms in the first place. Is that we need to focus on what is important by abstracting away low order terms and constant factors, and how we are able to indicate certain kinds of algorithms. Therefore, we need to develop or we need to formulate a way to compare size of these functions. So that there are some, as for big O is mostly referred to the smaller and equal. And there will be the omega. The big omega is the larger and equal. And theta means equal. And small o means smaller. And small omega means larger. And these are just the fundamental notation of the algorithm. So here comes with the big O notation. Big O notation, I think most of you have learned this from data structure, right? Or yeah, okay. So big O notation is characteristic as an upper bound on the behavior of a function. It says that a function grows no faster than a certain rate. This rate is based on the highest order term. For example, you can see that f of n equals to 7 n triple n and adding 100 n squared and minus 20 n and 6 is what? We can call that for the big O notation is O of n triple squared, and the highest order is 7 n triple squared. And therefore the function grows no faster than n3. So the function fn is, we can see that it is what? The function of f of n, it can be also write like this. This is Bradley constant if c is larger than 3. So big O notation provides an upper bound of the asymptotic behavior of a function. And here comes with the part of the omega notation. Omega notation is quite different than big O notation. Big O notation shows the upper bound. And as for the omega notation, it shows the lower bound of the asymptotic behavior of the function. For example, it is the same case, but it shows a lower bound of the behavior. So that since the highest order term n3 grows at least faster than n3, so the function of f of n is also n squared, omega n, and nc for any constant. C is smaller than 3. So here comes the difference is that big O notation is providing the upper bound, and the omega notation provides the lower bound. And here is the so-called theta notation. Theta notation is the height bound of the asymptotic behavior of the function. So it says that whenever a function grows precisely at a certain rate, again based on the highest order term, so that if a function is both big O of f of n and omega f of n, then the function is theta f of n. So you can consider it as the big O, and the omega, and the theta notation will be in the middle of them, and they are like the bound and the upper bound, and this one will be the at the middle. So here comes the sorting algorithm. So for I equals 2 to n, but what we want is to insert a of I in the sorted subarray. So here comes the pseudocode when j equals to I minus 1, and when j is bigger than 0, and a of j is bigger than n. So a of j plus 1 equals to a of j, and j equals j minus 1, and a of j plus 1 equals the key. It is quite easy. So any of you want to tell me what is the time complexity of the pseudocode? So whenever we want to analyze the pseudocode, and we want to analyze about the time complexity of the pseudocode, we can see that it runs in big O in n squared time, because there are a loop called for, and there is another loop called while. So the time complexity will be big O in squared time, regardless of the input. So the outer for loop runs n minus 1 times regardless the values being sorted, and the inner while loop iterates at most I minus 1 times, and the exact number of the iteration while the while loop makes depends on the value it iterates over, but it will definitely iterate between 0 and I1 times. Since that I is at most n, the total number of iterations in the inner loop is at most 1 n minus 1 multiplied by n minus 1, which is less than n squared. So each inner loop interaction takes constant time, and for a total of at most cn squared for some constant c, we can find out that the time complexity is big O n squared. Okay, so we got another case is that it is about the worst case running time of omega n squared. Here comes with so it is like we can observe that for a value to end up k positions to the right of where it started, the line aj plus 1 and equals to aj must have been executed k times. So assume that n is multiplied of 3, so that we can divide the array A into groups of A of n over 3 positions. So here is how we are able to describe it in the figure. Is that for A1 to n over 3 and A n over n over 3 and at 1, and we got 2n over 3 to 1. So each of the n over 3 largest value moves towards through each of these n over 3 positions, and to somewhere it shows the n over 3 positions. So because at least n over 3 values must pass through the least n over 3 positions, the line A of j minus j plus 1 equals to aj executed at least n squared over 9 times, where it is n omega n squared. For this input, the insert sort makes a time omega n squared. So we have, since that we have shown that the insertion sort runs in big O in 2n squared times in all cases, that there is an output makes it like take omega n squared time. We can conclude that the worst case running time of insertion is beta n squared. So the constant vectors for the upper and lower bounds may differ, and that doesn't matter. So what can you learn from this part is that no matter what you are using big O or omega or theta, the most important thing is that it doesn't matter which one you choose. The most important thing is that how you are able to destructuralize the problem. Okay, so here comes another example, is telling you about the big O notation. Whenever we talk about big O notation, all of G of n equals to the f of n, that there exists positive constant c at the n0 such that 0 is smaller than f of n and smaller than c multiplied by g of n for all n that is larger than n0. And here comes the gn is the asymptotic upper bound for f of n. So if f of n belongs to big O g of n, we write f of n equals to big O g of n. So for example, you can see that 2 multiplied by n squared equals to big O n3, and with c equals to 1 and then 0 equals to 2, the example functions is in big O n squared. So you can see n squared at n squared at 100, 1000 n, 1000 n squared at 1000 n, so that then we can find out the time complexity of the problem. And as for the part of the omega notation, is that we can find out that there exists positive constant c and n0, that 0 is smaller than cnj, that cg n, and smaller than f of n for all n bigger than n0. So g of n is an asymptotic lower bound for f of n. As for the part, it is quite similar as for the theta notation, is that there exists positive constant c1, c2, and n0, that 0 is smaller than c1 g of n and smaller than f of n and smaller than g2 c2 g of n for all n is larger than n0. So we can find out g of n is the atomically high bound for f of n. So we need to be careful to use asymptotic notation correctly when characterizing running time. Asymptotic notation describes the functions in which term describe running times, but you must be careful to specify which running time. For example, the worst running time for insertion sort is big O n squared, omega of n squared, and theta of n squared. All of them are correct, but prefer to use theta n squared here since it is the most precise one. And the best case running time for insertion sort is big O n, omega n, and theta n, and then we can prefer theta of n. But we cannot say that the running time for the insertion sort is theta n, because that is only when we talk about the worst case omit. Omitting the case means that making a blanket state that covers all cases, and the insertion sort does not run in theta n squared in all cases. What you can do is that you can make the blanket statement that the running time for insert sort is big O n squared, or that's omega of n, because these asymptotic running times are true for all cases. So for the merge sort, its running time is theta n log n in all cases. So it's okay to omit each cases. So there are some common errors. Whenever we are completing big O notation with theta notation by using big O notation to indicate an asymptotically type bound. Big O notation usually uses only an asymptotic upper bound, saying that an big O n log n time algorithm runs faster than big O n squared time algorithm is not necessarily true. An algorithm that runs theta of n time also runs in big O n squared time. If you really need an asymptotically type bound, then what you want to do is to use the theta notation. So use the simplest and the most precise assumptive notation that applies. So you need to suppose that an algorithm's runtime is 3n squared at 20n. The best to say is that it's n theta n squared. And you can also say that it is big O 3n squared because it is less precisely. You can say that it's theta 3n squared at 20n, but that obscures and the order of growth. So what we consider most is we consider how does your algorithm grows or the complexity grows by the exponential way. So you only need to find the largest exponential number of the equation. So whenever we talk about the right hand side, big O n squared stands for some autonomous function in the set of big O of n squared. So 2n squared at 3n1 at 1 equals to 2n squared at theta n, means that 2n squared at 3n at 1 equals to 2n squared at f of n for some function. You can see some function. F of n belongs to theta n. In particular, f of n equals to 3n plus 1. And that is from the right hand side. And as for the left hand side, you can see that no matter how the autonomous function are chosen on the left hand side, there is a way to choose the autonomous function on the right hand side to make the equation valid. So we interrupt 2n squared at theta n equals to theta n squared as the meaning of all functions. F of n belongs to theta n squared, where exists a function g of n belongs to n theta n squared such that 2n squared at f of n equals to g of n. So we can change it together, is that we can find out that 2n squared at 3n at 1 can be calculated like 2n squared at theta n. And then 2n squared at theta n is equal to theta n squared. So how we are able to interpret the first part. So the first equation tells you that f of n equals to theta n, which means that we can conclude that 2n squared at 3n at 1 can be written as 2n squared at f of n. We separate these two parts. And then we go to the second equation, is that for all g of n belongs to theta n, such as the function f of n used to make the first equation hold. So there will exist an h of n which belongs to theta n, that 2n squared at g of n equals to h of n. And that's how we can interpret the equation. So whenever we talk about the characteristic running time, we often abuse astounding notation when writing recurrences. So whenever we want to write the recurrences, is that t of n equals to big O of 1 for all n smaller than 3. And to be much more strictly to say about the situation is that this statement is meaningless. The definition of big O notation says that t of n is bounded above by a constant c when c is bigger than 0, for n is bigger than n0, and for some n0 bigger than 0. The value of t of n for n smaller than n0 may not be bounded. So whenever we say t of n is equals to big O of 1 for n smaller than 3, you cannot determine any constraint on P of n when n is smaller than 0 because you could have 0n which is bigger than 0. What we really mean is that there exists a constant c bigger than 0 such that P of n is smaller than c for n smaller than 3. So this convention allows us to provide naming the bounding constant so that we can focus on the more important part of the recurrences. So for the big O notation, you can see that the O of G of n equals to f of n for all constant c is bigger than 0, and there exists a constant n0 is bigger than 0, so that 0 is smaller than f of n and smaller than cg of n, and for all n bigger or equal than n0. So whenever we can use the concept of limit to find out that it will be 0 under circumstances. As for the omega notation, is that for all constant c bigger than 0, there exists a constant n0 equal bigger than 0, that 0 is smaller or equal than cgn, and smaller than f of n for all n bigger than n0. As for another view, again, it is very similar. We can find out that it is infinite to this by using the concept of limitation. So here we can compare of different functions. Is that we can see the transit. We can go through we can compare these by different way. The first way is that you can see that f of n is equal to theta g of n, and g of n equal to theta h of n, and which we can refer that f of n equals to theta h of n. So we find the same for big O omega and small o and small omega. As for the part of reflexivity, the part is f of n equals to theta of f of n. So we find the same as for big O and omega. Symmetry is that whenever we talk about f of n equals to theta g of n, if and only if g of n is equal to theta f of n. As for the transpose symmetry, f of n equals to big O g of n if and only if g of n is equal to omega f of n, and f of n is equal to small o g of n if and only if g of n equals to omega f of n. Yeah, these are just the basic comparison of these functions. So, at this case, we can say that f of n is asymptotically smaller than g of n if f of n is small o g of n, and f of n is asymptotically larger than g of n if f of n is equal to omega, small omega of g of n. So we can link it, big O to smaller and omega to bigger and equal. Unlike real numbers, where A is smaller than B, A equals to B, or A is bigger than B, we might not be able to compare the functions. For example, whenever one add sign and since that one add sign oscillates between 0 and 2. And here are some notations about the logarithms. So we got the LGN, it is quite easy. But for the binary log, we can see that LGN is the log by 2 and n, and log n equals to log e and n, and LGKN means that we got the log LGN of k and so on. So whenever we hold a b constant, the expression is restrictedly increasing as a increases. And whenever we hold an a constant, the expression is restrictedly decreases as b increases. So here are some equations. You can see that I think all of you have learned this in senior high school. Is that when a equals to b of log b of a, so it is quite easy because you only need to eliminate these two and then a comes to the front. A comes to the front and these two are ones. Is a minus a equal to a. And log c of ab means that we got log c a adding log c b. And as for the log c a of n, you can put the n square in the front, and then you see that we can refer to n multiplied by log b of a. And as for the part of log b of a, you can use it by log c of a over log c of b. As for the part of log b of a of 1 over a, you can use the minus sign in the front and find out the equation. As for the part, you can see that log b of a is the log a 1 over log a of b. And for the last but not least is a log b of c equals to c log b of a. Okay. So that is what we have. I think that's what we have learned in high school. But let's go over it quickly. So I think for this class, these are just some fundamental concept and recall of what you have learned in infrastructure. So I think we will stop here and take a break. So any questions? Quite easy, right? These are just some origins that we need to read in the first place. Okay? Okay, let's take a break.